Good morning, everyone. Thank you for your time. Well, my name is Luis, and until very recently, I was a postdoc at Macquarie University. But I would like to talk today about what I did in the last couple of years, and it is the numerical simulations analysis of dust formation in common envelopes. And here is a list of my collaborators, including Danny Price, Mike Lau, the former PhD Mike Lau, Ryosuke Hirai, and Thaisa Danilovich. Okay, so, what is a common envelope? Basically, a common envelope is a phase of evolution in binary stars that occurs when a giant star, in this case an AGB star, transfer material to a companion, and in this case is a compact companion, a main sequence star. The process of mass transfer is unstable. So at the beginning you have transfer of mass from the giant to the companion, but later you have the two stellar cores surrounded by the common envelope, and the interaction reduces the orbital separation of the binary system due to energy and angular momentum exchange. So that is in the theoretical part. In simulations, in numerical simulations, is we often have that the ejection of the envelope is not complete because there is not enough transfer of energy, momentum. So often we use we take into account recombination energy to unbind this envelope. And this is going to be important later. Let me, here, I don't know if you can see this. Oh, sorry. Well, this is an animation, a video made by Mike Lau of a common envelope. So at the beginning, you can see that there is a giant star separated by from the companion, but later the two stellar cores are surrounded by this envelope, and that is basically the common envelope, right? Now, why this common envelope is important? Why this phase is important? Well, that's because this phase is key, is really important for the formation of compact binary systems, for example, X-ray binaries or supernova type 1a progenitors, or even black holes and neutron stars binaries, which are sources of gravitational waves. So it's important to study this, but also because some common envelope interactions may produce luminous red nova that produce dust. So talking about dust, well, what is the role of dust in common envelopes? Well, on the one hand, dust can affect the common envelope dynamics because you are forming material with a higher opacity. So the radiation pressure in this material is going to accelerate and eject the material. But on the other hand, you change the appearance of the object because the material now is more opaque, has a high opacity, and is going to be really opaque in the optical, but more bright in the infrared wavelengths. So, well, if it is that important, previous simulations only consider one-dimensional models or make a post-process for dust formation. That is, they don't calculate the formation of dust in the simulation, but after. So they made estimates of what is the opacity, what is the mass, what is the temperature of these dust grains, but not a real, an actual calculation of the dust. So that's why in a previous in a previous work we made common envelope simulations, but taking a really simple approximation for the opacity of dust. And this is an analytical approximation in that the opacity is going to be high when the gas temperature is below a condensation temperature. If the gas is hotter than that, there is no dust. So it's as simple as that. The problem is that Well, what we found is that this new opacity, this new presence of dust do not affect the ejection of the material, do not help in increasing the mass loss rates. And the other thing is that with this approximation, you don't have properties like the size of the dust grains, or where is the dust form, or what are the properties. So with that in mind, the next step was to improve the calculations, but now making a self-consistent treatment of dust formation, where it forms, how it forms, what is the size, the amount of mass that is in the envelope. Okay, so now with the method as initial conditions, we take two AGB stars of different mass that were calculated using the MESA code, the stellar evolution MESA code, and we place the two stars so that at the beginning of the simulation there is a Roche law overflow. That is, the mass transfer begins immediately. We use the phantom SPH code for the simulations. We use 1.3 million particles for this, and we take into account in equation of state tables the recombination energy. So that will be important later in this talk. Okay, in this table, I show you some parameters of the models, and basically we have two models. One in which the AGB star has a mass of 1.7 solar masses. The other has 3.7 solar masses. That's basically it. The difference in all these other models is how we take into account dust. For example, here in the non-dusty world, there is no dust. These models that are called Bowen, this is the simplified approximation for the opacity, and that means what is the maximum amount of opacity. In this one, the maximum opacity is 5, and in this one is 15. And these dusty models include the full nucleation process, the full nucleation method. Here I show you initial and final orbital separation for the models, the percentage of unbound mass that at a specific point in time, and the amount of dust that is formed in these simulations. Note that the amount of dust is here is between 10 to the minus 3 and 10 to the minus 2 solar masses.
Which units are the opacities?
Sorry, it's square centimeters per grain. Yeah, sorry about that. Okay, so the dust formation, in this case, we focus only on carbon-rich dust formation. For this method, it's easier to work with this carbon-rich. Of course, that is a limitation because in AGB stars you can have oxygen-rich material or carbon-rich material, but we are just doing this, assuming that the gas has an abundance ratio CO of 2.5. This is high, of course, but it's based on some observations made by Ventura et al. In 2018. So this is a maximum, but it's a feasible maximum. And the purpose is to provide an upper limit of how much carbon dust can be formed. Okay, the method. The method is just a two-step process. The first step is a condensation of seed particles, the initial dust grains, in which the monomers are going to stick. There is going to be an aggregation of monomers, so the dust can grow to macroscopic size, and this is the growth phase. So to make this, to calculate this, we use the moments, the theory of moments developed by Gale in 1984, Gale et al. And it's based on these K moments, which are defined here by this sum. And the key point with these moments is that, okay, the key point of these moments is that you can calculate properties of dust. So, for example, the average radius of the dust particles, assuming that they are spherical, you can have it by dividing the first moment by the zeroth moment, or for example, the Planck mean opacity, taking the K3 moment, Or even, and with this opacity, you can calculate the radiative acceleration of the particles, including by equation 7. Yeah, so these moments are really important. And how do we evaluate the evolution of these moments is given by equations 2, 3, and 4. And the key point here is that in all of these equations, there is this variable J star that appears. But this J star is simply the formation rate. How many particles, dust particles, are formed per volume and per time. That is essentially this variable. So it's really important. I'm not going into the details of how do we calculate this J value, but I can show you, for example, what is the dependence, how does the nucleation rate depend on temperature and in pressure. So here, for this CO ratio, you have that the nucleation rate, this is the color map, lighter colors indicate a higher rate of formation, darker color indicates lower rate of dust formation. So you can see here that the formation of dust is important or is larger for a particular range in temperature between 1400 kelvins and 1100 kelvins. So it's a really narrow region of temperature. That is the sweet spot where the majority of new dust is formed. Sorry, I forgot to mention that also with the K3 moment, you can calculate, for example, the mass of carbon atoms, the dust, the total mass of dust that is in the envelope. And you can compare it, for example, with the theoretical maximum of carbon that is available to condense into dust. So if you compare these two, you can have later an approximation of the efficiency of the process. Okay, so this is the prediction. At least this is the theoretical prediction. But in the simulations, what you have in the two models, the 1.7 model, and the 3.7 solar mass model, is basically the same. The formation of dust happens when the temperature is around 1400 kelvins. This is the sweet spot. Temperatures higher than that, the dust formation is not going to occur as fast, and at lower temperatures is the same. So this is like the main result here. Okay, now this is a movie. No, this is a video of the formation rate, the nucleation rate to the left in the orbital plane for this model, the 1.7 model. And to the right is a movie of opacity. Darker colors indicate more material that is more opaque, and lighter colors, the opacity is lower. So you can see here, let me go back. You can see here that the nucleation rate, the formation rate, and the opacity is related. And it makes sense. If you are forming large amount of dust, then the opacity is going to increase. That is good. Okay, so but what is the difference in the dust distribution and in the opacity distribution when you compare the two models, the lower mass AGB and the higher mass AGB star? Well, this is the perpendicular plane to the orbital motion, the xz plane, and at a particular time after the onset of the simulation. So you can see here, for example, that for the higher mass AGB star, the distribution in opacity is more spherical. The high opacity shell is more spherical compared with the lower mass AGB star. And that is because the companion star, the gravitational effect of the companion is stronger in this case, because here you are considered, these two simulations have the same companion star. The companion star had the same mass, but here the gravitational effect by the companion is stronger. So the dust formation is going to be, the formation is going to be preferred along the equatorial plane. Okay, but this is with the nucleation model. What is the comparison with the Bowen simplify model. Well, here at the top you have the Bowen opacity in the orbital and in the perpendicular plane, and for the 1.7 solar mass, and at the bottom you have the nucleation model. So you can see here that with this simplified approximation, the problem with this approximation is that overestimates the opacity of the regions. For example, in the outer regions, the opacity is much larger, and also in the inner regions. There is only a tiny fraction, a tiny region where both models gives practically the same result. But why is that? The problem is that in the Bowen model, the opacity is constant. Once the maximum is reached, the opacity is constant, contrary to our models. In our models, because we are using the Planck mean opacity, that opacity is proportional to the temperature. So in the outer regions, the temperature is lower. In consequence, the opacity is going to be also lower. But there is, apart from this tiny region, tiny shell, where the opacity grows really high and peaks around 20 square centimeters per grain, the opacity goes down. So that's one of the reasons. Okay, here I show you a video of the opacity for this same model. And here I show you the nucleation time. This is the time where dust formation happens. Lighter colors indicate that the dust formation happens earlier in the model, and darker colors indicate that dust formation happens later in the model. So you can see here that the first dust grains have a decreased opacity, and at 40 years, all this material, the opacity of the material begins to decrease. And that's because the ejection of the envelope is complete, so the envelope is only cooling down. Okay, and this is again the nucleation time, a video, but for the dust size, the size of the dust grains. And you can see here, for example, that for the first dust grains, the lighter colors, the range in size is narrow, compared, for example, with at later times. You see that, for example, the dust particles can have up to 1 micron in radius. But this size, this distribution is not constant. The size of the dust particles is going to change based on complex hydrodynamical interactions in the simulation. But one thing is clear, is that all this material grows at least an order of magnitude in size. All this material grows until a certain point, and the size after that is constant. So the growth is limited when the ejection, the density of the ejected envelope decreases. Okay, and for comparison, this is the 1.7 model, solar mass model, the 3.7 solar mass model, and basically you have a qualitatively similar result. Here you have that at the beginning the range in size is narrow, but when after at later times the dust can have different sizes, and is around 0.1 microns. Okay, now in this plot I would like to show you the effects, for example, of the orbital motion in the dust formation process. Here is the 1.7 model, this is the orbital plane, and this is the perpendicular plane. And again, the nucleation time, darker regions indicate that dust was formed later. Lighter regions indicate that dust forms at the early moment. And you can see here for this model, these spiral structures. These are regions of enhanced density, where the formation of dust was favored, and this is because the orbital motion of the companion star. So here in this case, the binary have an effect in the dust formation process, and it's more evident here in the perpendicular direction, because here you see these darker regions, but that means in the polar direction you need to wait a little bit more for dust to form. that means because here the gas is preferentially ejected near the equatorial regions, then the density here is higher, the formation of dust happens earlier, but here no. You need to wait more for dust formation. But it doesn't happen the same with the more massive AGB star. Here the distribution in the nucleation time is more rounded, more spherical, and that means that here the effect, the gravitational effect of the companion star is not so strong. And at the end, you will have a more or less rounded distribution of dust. Okay, let me tell you about the total dust, the total amount of dust in the envelope. So here are our two models, the 1.7 solar mass and the 3.7 solar mass AGB stars. The dashed lines are the calculated amount of carbon, and the horizontal lines is the theoretical maximum. So you see, the first thing to notice is that in less than 40 years, you are forming almost all of the maximum in dust. You can form all of the available carbon is into dust in 30 or even 40 years. But also the scale. This is 10 to the minus 2 0.02 solar masses, or even close to 0.01 solar masses. So 10 to the minus 2 solar masses of dust in less than 40 years. So that's a huge, that's really fast, and that can have significant consequences for the appearance of an object. You are forming such a high amount of dust in so little time. Okay, and what about the orbital evolution? What happens when you consider dust formation in the common envelope? Well, you can see here the different models. The one with nucleation, the other, the yellow curve is with no dust, and the other two, the red and green, are with the Bowen, with the simplified assumption in the opacity. Despite what you can see here, dust is not the cause, is not responsible for this change in the orbital evolution, and that is because in the radiative acceleration, we are also considering the gas opacity, and it is small, but it seems that in the early phases of the common envelope, the conditions, the system is sensible on the initial conditions. So little changes in the dynamics of the common envelope can have significant consequences in the orbital evolution. But I'm going to show you why is that this, the dust is not forming in regions where orbital motion happens. And here I show you the bound mass, the amount of bound mass in the common envelope as a function of time for the two models, the 1.7 solar mass and the 3.7 solar mass. And here again, you have the nucleation models, the common envelopes without dust, or the Bowen simplified assumption. Here you can see, well, the solid lines indicate a criterion, a mechanical criterion. I'm going to describe to you later this mechanical criterion, but you are going to consider that the mass is unbound if the total energy, kinetic and potential, gravitational potential energy is larger than zero. If that is larger than zero, then that gas is unbound from the system. But in the thermal criterion, apart from kinetic and gravitational, you consider the thermal component of energy. So you can see here that if you compare the dashed lines with the solid lines, the change is more evident. So the effect of recombination energy, because recombination energy is included in the thermal component, has a larger effects on the unbound mass. And why I say this is because we calculate the total energy of the SPH particles with dust formation at different times from beginning to end of the simulation. And you can see here that the total energy, kinetic, potential, thermal, of these particles is larger than zero. So at the end, you are the main result is that dust is forming in already unbound regions. So the effects of dust formation for the evolution of bound mass is minimal. There is no effect. But this is because we are considering recombination energy. Okay, now another result. Now with the observable properties. In this case, we have again the 1.7 and 3.7 models, but one of them had dust and the other is the non-dusty simulation. You can see here that the blue lines, the size of the photosphere as a function of time for the dusty simulation is larger by almost an order of magnitude. That is, you will have a photosphere almost 10 times larger, and it is the same for the two models, for both models. So the presence of dust changes the appearance of this object. And of course, we are calculating the optical depth here. So if you are including more opaque material or material with a higher opacity, then the optical depth is going to increase. And this is a plot of the photosphere for the two models in the orbital plane, the perpendicular plane for the 1.7 and 3.7 solar mass. And you can see that after 40 years, well, close to 43 years, the photosphere of the common envelope is more rounded. So for this case, for these two cases, the companion, the companion star is not affecting the distribution in the dust formation. Okay, so now that I talk about the results, let me talk about the discussion and the limitations in the current models. One of the limitations is that we don't have a proper treatment or radiative transfer in the simulations. And that is important because we are including recombination energy in the envelope, but all of this energy is included in the thermal component of the envelope. And what happens, for example, if we allow that 50% of the energy escapes through radiation into space, maybe the dust is going to form in regions closer to the binary stars. So another limitation, for example, is that the gas and the dust temperatures are equal in this case, and that might not be the case. So what are the effects if we consider different temperatures in dust and in gas? And for example, if we include radiative cooling, maybe the condensation temperature, the gas reach condensation temperatures in regions closer to the binary stars, and because in those regions the density is higher, maybe the rate of dust formation will be higher. So that means that maybe if you include radiative cooling, dust is going to form faster. Another thing is that we consider a constant luminosity for the star, so the radiative pressure keeps the same value. And we also consider an optically thin envelope. The radiation that hits the dust grains is the direct stellar light. Also important, we do not consider grain destruction mechanisms. So that's why the efficiency of this nucleation process is 100%. But that might not be true. Maybe the destruction processes are really important. And as an example, the overdensities in the spiral shocks might be more important when you allow dust destruction. Maybe the shocks are too strong for dust to survive in those regions. And again, we do not calculate oxygen-rich dust. This is only limited to carbon-rich. So if you want to consider RGB stars or oxygen-rich AGB stars or even red supergiants, well, you need to wait. You need to wait a little bit longer. Okay, so comparisons with other models. These authors, Glantz and Perez, in 2018, made analytical estimations, or the dust condensation radius. So they made these certain assumptions and calculate where the dust is going to form. And their values or their results is that if we use the formulas, the formula that they made, that they derived for our model for the 1.7 solar masses AGB star, the condensation radius is close to 5 astronomical units, or in the case of the 3.7 AGB star, the condensation radius is close to 7 astronomical units. But that is in the estimation, in the analytical estimation. In our simulations, the dust begins to form at 10 or 20 astronomical units, 2 or 3 times farther away. So this approximation underestimates the radius, but that is because in this work they did not consider recombination energy. So there might be larger differences with this term. Okay. Now, what happens with possible observational counterparts? One of them is string carbon stars. Some of them are detected in the Large Magellanic Cloud, but they have mass loss rates of 10 to the minus 4 solar masses per year, and this is really high. This is larger than what is expected for single stars. So this author and these authors, they made calculations, or they made observations, sorry, and they derived luminosities for these stars of 5,000 or 10,000 solar luminosities with effective temperatures of 300 kelvins. So that means that the implied photospheric radii is between 100 and 200 astronomical units. And that is similar to what we derive in our simulations. The radius is similar. So if we take that into account, together with that in the simulations we are ejecting in approximately 20 years 10 to the minus 2 solar 10 to the minus 2 solar masses of dust, then this amount of dust is going to contribute to the optical appearance of the object, and maybe because all of that, we can consider that these extreme carbon-rich stars are outcomes of common envelope interactions. Or the same might happen with water fountains, which are oxygen-rich AGB stars, but they have optically thick envelopes, dusty envelopes, in a torus shape. But the problem is that for water fountains, the material, the structure, the dusty structure is like a torus, and not and that is different than in our simulations, because in our simulations we have an spherical structure, an spherical dusty structure. So maybe we need to consider more massive companion stars, a different combination of stellar parameters for this. So finally, in conclusions, well, we made these two common envelope simulations, taking AGB stars of different masses. And in both simulations, the dust formation starts at about 2 or 3 years after the onset of the simulations. And also the dust formation, the dust grains are small, have a small radius, but they grow in size due to the addition of monomers. And at a certain point, when the density is low enough, the growth stops. There is no more aggregation. If we do not take into account the destruction process, the dust formation is 100% efficient. So that is an upper limit. And again, in our simulations, dust formation does not lead to substantially more mass unbinding. And that's because even if we are forming this amount of dust, the regions, the envelope is already unbound when dust forms. Now, we are forming in less than 40 years 10 to the minus 3 or 10 to the minus 2 solar masses, and that has a huge impact in the optical properties of the stars, for example, in the effective radius in the photosphere. Or also that the morphology of the envelope is nearly spherical. But again, we maybe need to consider different configurations, different orbital and stellar parameters. And because we are producing dust in less than a century, in 20, 40 years, this carbon dust is going to affect the appearance, but maybe can be identified or can be identified as these carbon-rich objects or water fountains. So now that with this work, the future prospect or the next steps will be, for example, what happens if we include radiation transport or radiative cooling? Maybe the formation of dust is going to happen faster. Or what happens if we include more massive companions? Or what about oxygen-rich? This is the most important question. What about oxygen-rich dust formation? And we are working right now in this aspect. So that will be it for my part. Thank you for your time.
Initially, you had the Bell model, which had like a maximum cutoff for the opacity, and then you improve on that with using some Planck means, right?
Yeah.
So is there a particular reason why you actually work with Planck means and not like some other precision like Rosland or whatever?
Yeah. Well, based in this model is because you can have, when you make the Planck mean, you can relate the opacity with the properties of the dust. For example, with the size distribution, with the distribution of size. So is a direction, and the one of the moments, the moments per se, are based in this size distribution. So it's an easy way to relate opacity with the properties of the dust grains. But of course, this is an improve, because in this case, well, in the simplified approximation, we only consider temperature as a function, the opacity only as a function of temperature, nothing else. But here we are calculating the rate of dust formation, the size of the dust, and based on the size of the dust, we are also calculating the opacity. So we are taking into account the thermodynamical conditions in the envelope to calculate the opacity.
So maybe I'm misunderstanding something, but it looks like the total amount of dust that you're forming is less than the difference in the amount of unbound material between your dusty and non-dusty simulations, right? So if I look at the difference, for example, between in this table, between the first line and the third line, right, in this table,
okay,
the unbound mass, it differs by 0.08 solar mass.
Okay.
More than the amount of dust that you're forming. So that seems strange that forming a little bit of dust can change the amount of total ejected by a larger amount than the total amount of dust formed. So I'm trying to understand why that's happening.
Okay. Well, maybe the confusion here is, well, I didn't say this explicitly. This amount of unbound mass is at a particular time in the common envelope simulation, is about 12 years after the onset of the simulations. But this is because we need to compare with the previous simulation, because the simulations there, only the total time of computation was 12 years. But in the dusty simulation with nucleation, we are calculating for more than 40 years in that simulation. And in that case, the amount of unbound mass is close to 100%. So in this case, the recombination energy is making a bigger change is the effects of the recombination energy are larger, for example, than the formation of dust. And the other thing is that because, for example, let me show you. This one, this plot. In this plot, I'm showing all the particles at different times in the simulation where dust is happening. But here, the material is unbound. So because the dust is unbound, or well, the regions of dust formation is unbound, the mass loss rate is doesn't change. Actually, the dust is forming too far away to make a significant impact in the amount of unbound mass.
Thank you.
Yeah, thanks for the talk. I know that for this research you worked on, you looked at carbon-rich dust. I'm interested in if you had any suspicions on how oxygen-rich dust would change your results, because I know they're probably more oxygen-rich AGBs than.
Yeah. Well, the short answer is that the condensation temperatures of oxygen-rich dust is lower. For example, carbon-rich can have condensation temperature of 1500 kelvins, maybe up to 16 or 1700 kelvins. But oxygen-rich is silicon, it's based on silicon. So the condensation temperature is only 1000 or 900 kelvins. So it's significantly lower. So that means that dust is going to form at regions farther away from the binary stars. If that happens, because the density in that regions is lower, then the formation rate might be lower also. And finally, you are going to form dust, but at a lower pace, or maybe even less dust than what you can have with carbon-rich dust. So that's my initial guess.
Have you tried using maybe other metallicities for the models, and if not, what would be your expectation?
Yeah, of course. Maybe because this was an initial step, but of course we are planning on make new simulations. Here we made with a CO ratio of 2.5. We are going to consider a CO ratio of 10, which is really extreme. But we are going to see if there is any limitation, for example, in metallicity and the amount of carbon that is going to be formed. Here we show that the efficiency is close to 100%. So maybe if we increase the amount of available carbon, the metallicity, we are going to form more dust. But or maybe the CO ratio is really high and the efficiency is not 100%. But at the moment, I expect that if you increase the metallicity, the amount of dust is going to increase also.
Okay. And if you reduce it, will you still have very good efficiency in forming dust, or you will have some? It's like it's a critical mass, critical metallicity fraction to be efficient.
Maybe I wouldn't be surprised if the efficiency begins to decrease after a value of the CO ratio, because not only depends on the amount of carbon, but how the material is ejected. So if you eject this material really fast, maybe the formation process is not going to be as efficient as in this case. But yeah, that is also an important parameter to study.
Yeah, it's a nice thing to kind of like pinpoint if this exists, to kind of find this point where this happens, because it could have a lot of implications for low Z environments like old clusters that people are studying here.
Yeah.
I don't know.
Yeah, that's right. That's right.